In this problem, it says we decide to roll 5 6-sided fair dice. And what is the probability that you get at least one number 3 out of the 5 dice? Now, anytime you see that at least one, it should send off bells in your mind saying, use the complement rule. Now, so that's what you want to do. This video, though, I'm going to go into a little bit more in depth of why do we use that complement rule. So when you think about rolling your 5 dice, what if we listed out all the possible outcomes? So like I could roll, I'm going to use an N here for not 3. So N for not 3, because everything is either going to be a 3 or not a 3. We don't really care what else it is, just that it's not a 3. So you could get a not 3, not 3, not 3, not 3, and not 3. Or, so this one would, if we say X is the number of 3s, this would be X equals 0. There are 0 3s. My next one, it looks like there's 1, 3, and then not 3, not 3, not 3, not 3. So like X equals 1. My next option, not 3, then not 3, not 3, not 3. That would also be X equals 1. Or I can have this option for X equals 1. And so as we go down through this list, notice there's different ways to get like X equals 1. But now I switch and I start getting like 2 3s. So this would be X equals 2. And this next one would be X equals 2, etc. And you keep going. So this is all the possible outcomes, because when you get 1 3, it could be the first 3, or it could be the second 3. So it could be the first one, or the second one, or the third dice, or the fourth dice, or the fifth dice. Because if you're rolling 5 dice, you could get that 3 on the first one, second one, third one, fourth one, or fifth one. All of those would give you 1 3. But now to get 2 3s, well, it could be maybe like the first and second dice, or it could be the first and third dice, or the first and fourth dice, or maybe like the second and third dice, etc. There's a lot of different ways that you can roll 5 dice and get 3s or not 3s. And in fact, it turns out that there are 64 outcomes here. Now, I don't really want to try and find the probability of all of those. That's going to be a lot of probabilities. 63 of them have at least 1 3. So if I wanted to find the probabilities, I'd have to find the probabilities for all 63 of those and add them up. Or you could use the binomial probabilities. That would make it easier, but I'd still have to find a lot of probabilities, because the probability that X is at least 1, well, that's really equal to the probability that X equals 1, which is all 5 of these outcomes added together, plus the probability that X equals 2, which was here on down, plus probability that X equals 3, plus probability that X equals 4, plus the probability that X equals 5. Even if I use the binomial distribution, I don't want to have to go through and find all 5 of these probabilities by hand. That just takes way too long. I can do it, I just don't want to. So anytime I see at least 1, I have those bells that go off in my mind, and I say, hey, don't find all 63 of these probabilities, or all 5 of you use the binomial probabilities. Use the complement rule. So the complement rule says, well, if 63 of these have at least 1 3, what's the only one that doesn't? The only outcome that doesn't have at least 1 3 is this one. And so I could find that probability pretty easily. So the probability of at least 1 is always going to be equal to 1 minus the probability of none. Well, how will I find that probability of none? To get no 3s or none 3s, I would have to have a not 3, and then I would have to get another not 3, and another not 3, and another not 3, and another not 3. Okay. Well, the probability of a not 3, let's come over here and do that here. So the probability of getting a 3 is 1 out of 6, which means the probability of a not 3 would be 5 out of 6. Okay, so if the probability of not 3 is 5 6, then over here for the probability of not 3 and not 3 and not 3, we'll do 5 6 times 5 6 times 5 6 times 5 6 times 5 6. or 1 minus 5/6 raised to the 5th power, which equals 0.5981. So that's the complement rule. Makes it much, much easier than finding all 5 probabilities. Now, just as a side note, you might wonder something like, why is it not 1/3 to the 5th power? Well, 1/3 times 1/3 times 1/3 times 1/3 times 1/3, that is actually the probability that x equals 5. This is the probability of rolling a 3 and a 3 and a 3 and a 3 and a 3. That'd be the probability of getting 5 3s. So that's not what we wanted. We wanted the probability of 1 or 2 or 3 or 4 or 5. So that's why we had to go through all of this other work.